Yeah, first of all, shout out to Henry who couldn't make it because he's stuck in Ireland. There's snow. His flight was cancelled. He has a poster about his submission to the challenge I'm going to talk about right there in the corner. So if you want to learn more, please have a look. So what I'm going to talk about is generating natural language from structured inputs, which was part of the end-to-end natural language generation challenge, in which we were given a number of attributes, for example, the name of a restaurant, in this case, the Golden Palace, as well as human-created references that talked about all of these attributes without any embellishment. So it was very focused on just those attributes. And the challenge's goal was to basically replicate those human references, learn from these inputs to generate the text. So there were a couple of challenges with just a number of attributes that I wanted to quickly touch upon. The first one is that not all of these attributes always occur for every training point, which means you can have any number of the attributes listed here for any of the points or as input. So there are some of the data points that talk about an area and the name of a restaurant. There are some others that talk about the name, the type of the food, and whether the restaurant is family friendly. And you had to learn and to train a model that was capable of combining all of these. And in the end was evaluated on a test set that showed previously unseen connections or combinations of inputs, as well as previously unseen names of restaurants, previously unseen areas, and so on. Additionally, there were two more difficulties. First of all, you can see that some of the values for the attributes are multi-word. So you can have the city center as 2 words or the riverside as a single word. And sometimes some of the attributes even had completely different expressions. If you look at the price range, the very bottom one, you can have expressions for the price range of, for example, less than 20 pounds. Some of them were in between 30 and 40 pounds. Or you can have simple expressions such as cheap. And the model had to learn how these connect. And so just because not all of you might have heard of how natural language generation typically works, there are 3 steps that traditional systems all have. The first one is the content planning stage, which in this case is done for us, in which a system would select the content it wants to generate text about. In our case, we have the attribute value pairs, which represent the content planning stage. At the second stage, we have the sentence planning, in which the model, or traditionally the models would select a number of those attributes and put them into a plan of different sentences, order them, and, for example, decide which words would be part of a noun phrase or which one would be expressed as their own clause. Then from this abstract concept of a sentence representation, you would go to the service realization, in which a model would choose the syntax, the morphology, the orthography for the natural text. And you can see some of the differences in the different stages because the data set is actually multi-reference, so we have multiple references for the same input. So if you look at the first 2, they're both talking about the input about a restaurant named Alimentum in the Riverside, which is not family friendly, but is near Burger King. And you can see in the first 2 examples, in one part it has the does not allow families as its own clause. In the second one, it has the non-family friendly establishment as a noun phrase. In yet another example, we can see that it actually breaks up into 2 different sentences. Or if we look at yet another example, which is why data cleaning is really important, Alimentum across from Burger King, no kids, that might be something you don't want to generate. And I will get back to how our model does with those specific instances in a bit. But first we need to somehow squeeze this problem into a sequence-to-sequence setup that we can actually solve with OpenNMT. So what we did was we introduced a start and an end token for each of the different attributes. In our case, we have an example of the area, which as in the data set is represented as area city center, we would now represent as start area, city center, end area, and then concatenate all of these different representations in order to get the final sentence. And we did this while not altering the ordering of the different attributes, so that the model learns to also take advantage of whether or not an attribute might appear in between two others. So if we now have an input sequence and an output sequence, we can cast this in the typical sequence-to-sequence framework, where we have aligned source and target pairs, X and Y in this case, and we can use this to minimize the risk or to maximize the probability of the target given the input. So for the very vanilla sequence-to-sequence approach, we do not divert from the model you are used to from machine translation, and we have encoder and decoder as RNNs, although we have also tried the transformer model with quite some success. And we compute the attention as the softmax over the dot product between the hidden state at a decoder position and individually all the encoder positions. And then compute the context as a sum weighted by this attention. And after a final nonlinear transformation, we can get the word generation as a softmax over yet another linear layer. So far, there is no difference to traditional machine translation approaches in OpenNMT, but we can do something more. For example, you notice that words are often or always copied from the source into the target. If we talk about a restaurant, The Eagle, we always want to copy the words The Eagle into the generated text. So what we're using is this notion of copy mechanism that is also very popular in abstractive or in neural summarization models, which you'll hear about in a bit. So I don't want to go too much into detail here, so as to not bore you because it's already almost 6. But the idea is that we introduce a binary variable z for each decoding step that is basically a switch between generating a word or just copying a word from the source. And z is computed such that we have this generation probability, PZT here, that basically is the probability of copying a word. So if we want to have the final probability over all of the words, we just take the sum of the distribution over the vocabulary and the distribution over the source words. Another advantage here is that we don't actually have to have the particular source word in our vocabulary, which is really helpful for if we have little training data or if we encounter rare words, for example, restaurant names. So the way we compute the copy distribution in OpenNMT is we take the output of the attention layer and throw it into basically the same layer again with its own parameters. So we again take the dot product between the output of the attention layer and all the encoder hidden states. We compute and this time we don't compute a softmax. We compute a softmax over this, but we don't have to do this weighted sum anymore. We already have our context. And then we take the output of the attention as input to the computation of whether we copy or not as well. And then do this weighted sum of the two distributions. So we did this and found one other particularity about this data, which is that if we train the model, decode from it, it is now missing attributes. So especially in the validation data, where we have previously unseen combinations of inputs, we see that the model is frequently missing a lot of them. In this case, we have 8 different inputs, and the model is only generating a sentence about 4 of them, which is not good and not desirable, and we want to prevent this. So what we're using is actually the same penalty from machine translation from the Google NMT paper, because they introduced a coverage penalty, which aims at spreading the attention equally over all of the source words, which is exactly what we want, because we want every word to be copied exactly once. And the start and end tokens we want to be at least attended to, because we want the the model to know to generate about a certain aspect. So this is the same definition as from the original paper. And we also want to normalize by the length of the generated text, because generated text has the particularity that since we are scoring total likelihood of a target sentence, that shorter sequences are always better than longer sequences, because if we're adding up a bunch of negative log likelihoods, it will just get more negative as we add more words. Therefore, we also normalize by the length. We also use the same length penalty from the Google NMT paper. And now it should work, right? Well, except now we encounter this phenomenon that I call template hallucination, where the model is actually not really learning what we want it to be, because it sometimes associates certain inputs with wrong outputs. In this case, we are talking about a high customer rating as input, but if we look at the output, it is actually generating 3-star. In the context of this data set, 3-star is not 3 Michelin stars, 3-star is 3 out of 5, which is not a high rating. So we were curious why this would happen, and we investigated the training data. And we saw that the phrase 3-star occurs 271 times, and it is always in the context of average rating. So why would this ever happen? Then we looked further and searched for the phrase expensive 3-star, and we saw that it occurs 4 times. So somehow this entire model was thrown off by seeing an example of expensive 3-star 4 times. And we needed to build our model a little more robust towards those outliers, especially since we were talking about only 50,000 training points. So there are quite a few outliers that can influence the model quite a bit. And we use a technique called diverse ensembling. Diverse ensembling is typically the idea of creating a set of diverse models in order to create diverse text. We actually use the same technique in order to create a more boring model. So what we want is not diverse models. We want one model that is really good at following a really boring template structure. And the idea of diverse ensembling is that we first create k separate models, but instead of just training k separate models as we would in normal assembling, we also assign the data points to the individual models. So each data point has exactly one of the models. And we jointly optimize this assignment and the parameters. Or to be more formal, we introduce a variable, categorical variable w, that for each data point that basically states which model is being used for this data point. And now our overall objective is disjoint optimization. We optimize this with a stochastic multiple choice loss, which means that we only update one of the models at a time. So this is similar to a hard EM, where we would first do an E step, which is do a forward pass through the model, through all of the models, compute all of the individual losses of the models, then select the one that has the best loss. And then the M step would be just update that one model, ignore all of the others. So we can also be a little more smart about sharing parameters between models. So in this case, I've just drawn up one single encoder, but we have 2 decoders. And now we finally get to the point where I can say that we were actually doing quite well in this challenge. So we were first in 3 out of the 5 automatic metrics, top 5 in the 2 others, out of 70 total submissions. And we also evaluated and did an ablation study, and we see that all of the 3 facets of our model that I was talking about actually have quite a big impact on the final evaluation. We also did some more investigation of the multiple choice loss, where if you look at the bottom, we increased the number of models we were doing, we were looking at, and with just a single model, we don't have a good score. Increase to 2, we get a good score. Increase to 3, we have not really an improvement, because at some point the data gets too sparse. Then we looked at updating the top 2 models, not just the top 1 model, and we actually see quite a bit of an improvement. However, we could not see an improvement when sharing parameters between models, which suggests to us that they're actually learning quite different things, and sharing is not too beneficial. So to conclude, we First of all, we observed that sequence-to-sequence models with a copy mechanism can effectively generate short text about a number of structured input attributes. Then the coverage and length penalties lead to less ignored inputs, which is quite desirable as well. And finally, the multiple choice loss helps the model to better learn this latent sentence plan or this underlying template, and makes the model more robust towards those outliers, because we can just learn another model or train another model to pay attention to those, and have our main model just learn the core data points in the data set.